All right, let's dive right into an explainer on a classic computer science problem that is absolutely going to stretch those recursive thinking muscles of yours. If you're used to just iterating through arrays, trees demand a completely different mental framework. So today, we are exploring a really famous challenge, finding the diameter of a binary tree. And we're not just going to jump straight into writing code. No, instead, we'll use a Socratic approach, basically asking ourselves the right questions to naturally uncover the absolute perfect solution. But before we even think about touching an algorithm, we really need to lock down exactly what quantity we're trying to find here. It is so incredibly easy to just start coding before you actually understand the core of the problem. Like, what exactly is the diameter of a binary tree? And why does trying to find it trap so many developers into writing just horribly inefficient code? Well, let's figure it out together. Okay, here's our baseline definition straight from the problem statement. The diameter is the longest distance measured in the number of edges between any two nodes of a binary tree. Just think of it simply as the longest path you can trace from one node to another without ever lifting your pen off the paper. And notice that it specifically says measured in the number of edges, not the number of nodes. That's a tiny detail, but it's an absolutely crucial one. So if we look at a really simple 5-node tree, we can trace a couple of different paths to sort of pressure test our definition. Consider a tree rooted at node 1. It has left and right children, 2 and 3. And then node 2 has its own children, 4 and 5. Now just visually scanning this, try to find the absolute longest path from one end of this tree to the other. Right, so the crucial takeaway here is that the longest distance is exactly 3 edges, and your brain probably naturally traces it right up through the top root node. You could start at node 4, go up to 2, up to 1, and then down to 3. Boom, 3 edges. Or you could start at node 5 and do the exact same thing. Either way, both paths give us a diameter of 3. Our definition is holding up perfectly. Now, here comes our first real Socratic question. In that example we just looked at, the longest path passes right through node 1, right, the topmost root of our tree. And because of that, it's incredibly tempting to just assume the root is the hinge point for the longest path in every single binary tree. But let's pressure test that theory. Does the diameter absolutely always have to pass through the root node? Well, let's look at a skewed tree. Imagine node 2 has these long chains hanging off both its left and right sides. Here, the root is node 1, but it only has a left child, node 2. Node 2, however, is a pretty busy intersection. It has a left child, 3, which has its own child, 4. And it has a right child, 5, which has a child, 6. Take a quick second and try to trace the longest path here. And this brilliantly illustrates our very first trap. Rootness is a complete red herring. Our assumption was that the longest path must pass through the root. But the reality? The longest path is actually from node 4, up to 3, up to 2, down to 5, and finally down to 6. That is 4 edges. And guess what? Node 1 isn't even on that path. Node 2 is the actual hinge point of our diameter here. So if literally any node can be the hinge point, we need to understand what makes a hinge point special in the first place. Look closely at those chains hanging off node 2. What specific mathematical property of those two subtrees, measured as some kind of number, actually dictates that the path length passing through node 2 is exactly 4? Now, the real breakthrough here is the realization that depth is the absolute magic metric we're looking for. The length of the path stretching down the left side and the length of the path stretching down the right side, those are simply the depths of those respective subtrees. It's really that simple. Let's pin this down precisely. The depth of the left subtree, which is rooted at node 3, is 2. The depth of the right subtree, rooted at node 5, is also 2. So we've just found our core mathematical relationship. The path length through any given node is simply the depth of its left subtree plus the depth of its right subtree. 2 plus 2 equals 4. But here's where things get super tricky, and honestly, where a lot of algorithms just break down entirely. We need to check this math for every single node in the tree. Because remember, we don't know in advance which node is the true hinge point. If we use a separate depth finding function at every single node starting from the top and working our way down, what happens? We fall headfirst into a tragic big O of n-squared trap. We'd literally be asking for the depth of the bottom leaves over and over and over again for every single parent node above them. And the instinct to avoid that redundant work is exactly what separates a brute force answer from a really elegant linear time solution. As our source material highlights, we absolutely shouldn't call max depth top-down at every single level.
Instead, a bottom-up approach, or what we call a post-order traversal in the biz, is our efficiency savior here. By starting right at the leaves and working our way up, we can compute everything in a single, beautiful pass.
But wait, we've hit a bit of a structural wall in our logic. A recursive function needs to return its maximum depth to its parent node so the parent can do its own math, right? But if the function is only returning depth, how do we remember the actual diameter, the maximum path length that we might have discovered deep, deep down in the tree? We basically need the function to tell the parent node one thing, but remember a completely different thing for our final answer.
So to solve this, we have to cleanly separate our concerns into two completely different tracks. On one track, we have what we return up to the parent, which is maxDepth. That's purely used so the parent can calculate its own depth. On the other track, we have what we monitor globally, path length. Every single time we visit a node, we calculate the path length through it, compare it against the global best so far variable, and then update that global variable if the new one is bigger. Then the individual node's path length is just discarded, and the function returns the max step upward.
Now, to build this single recursive function, we just need to anchor it with some really solid base cases. When our function reaches the absolute bottom, what does it report back up? Well, if it hits an empty tree, a null node, it simply returns a max depth of 0. If it hits a leaf node, which is exactly one node deep, it returns a max depth of 1. And these base cases are the solid foundation that the rest of our upward math is built upon. So let's put this all together and see how it builds our complete plain English algorithm. Step 1, visit a node and recursively grab the max depth of its left and right children. Step 2, calculate the path length through this current node by adding those left and right depths together, and update the global record if this is the biggest path we've seen yet. And finally, step 3, pass your own depth up the chain to your parent, which is simply 1 plus whichever of your children was deeper. All right, moving into the final solution, let's look at writing the actual Python code. Now that we've Socrated our way to the perfect bottom-up architecture, we have everything we need to translate this beautiful logic into a working script. We're going to start by defining our class. Right at the top, we set up path length equal to 0. This is our global tracker, the variable that will quietly remember the biggest diameter we find anywhere in the entire tree. Then we have our main function, which kicks off our recursive traversal by calling our helper function, and then simply returns that global path length at the very end.
Now let's look at the real engine here, the maxDepth helper function. Inside, we first handle the empty tree base case. If not root, return 0. Then we immediately dive all the way down to the bottom of the left and right subtrees. We are calling our self.maxDepth recursively here, which effectively tells the code, hey, go find the absolute bottom before you do any math whatsoever. And once we hit the bottom, the code starts bubbling back up and we perform our dual-purpose magic at every single step. First, we update the global diameter. We check if the path through the current node is a brand new record by comparing our current path length against max left plus max right. Then, immediately after that, we return the deepest path back up to the parent node, which is 1 plus the maximum of those left or right depths. And just like that, we've completely solved it in a single big O of n pass without doing any redundant work. This pattern, returning one value up the recursive chain while secretly updating a global tracker behind the scenes, is absolutely incredibly powerful. So, I challenge you. Take this dual tracking mental model and see what other recursive tree puzzles you can easily break wide open. Because once you see it, you can't unsee it. Until next time, keep exploring.